everyone, me is here. Today I will present on Project 4, Dynamic Calibration and Epipolar Geometry. It has three parts. The first part is to calculate the projection matrix. This part is specified in the document that we need to solve this equation, this matrix equation, and then we can get a 3x4 matrix. And correctly calculating this matrix will give us a low residue and strong correspondence, like this. And you see all the points correspond to the point, actual points corresponding to the project point in this graph, and all the point on the right hand side graph is perpendicular to the projection of the plane. And here is the result of my first part. It has total residue of 0.0445, which is really small. And the second part is a fundamental matrix. This is solve the equation P prime Fp equals 0. And we need single value decomposition for this test because we need to solve the equation that equals 0. So we cannot use matrix division because we cannot divide a matrix by 0. And we use single value decomposition, aka SVD, and we also need to reduce the rank of the F so that I can make the determinant of F equal to 0. The F matrix enables us to draw an epipolar line in right image correspond to point in left image. I will explain this later in the other slides. So one big technical difficulty or the challenge is to reduce noise reduction, because like if you capture the point that is way off the correspondent points, and it will generate noise. They are not exactly project to each other, so some of them I will show you with an example. So here is the sample image epipole with noise induced in this example. You can see some of them, like the left hand side, it don't have much variance. It still looks relatively good, but on the right hand side you see it's there's a cross in the all the line cross at some point. That is not a good result that we want, and also those lines are not passed through the point that show on the red dot on the sample image. So noise can cause a lot of trouble when you want to calculate the fundamental matrix. It distorts the points that is correspond to each other point in the left and the right frame. So the task is we need to normalize the points. Here we induce a norm point function which calculates the points transformation to a new coordinate with a range of negative square root of 2 to the positive square root of 2, and we have the it calculates the transfer points and the transformation matrix, so we can get back where we had for the original image, the point correspondence. So here is an example of how this works. Basically, the input data is points corresponding to the coordinates in the image, and it's roughly it has a large variance because it's based on the units of pixels. For example, it has 882 pixels. It will have a numeric value of 800 and something. So basically that's very large, and a slight of variance in this numeric value will have a huge impact on the matrix that we calculated, and how we normalize it so that it's shrink into a small space that is from negative square root of 2 to the positive square root of 2, and it's a small space that we can manipulate, and the noise is also shrink to 100, so it's relatively small that we can ignore it in this way. So here is the transformation matrix. Here is the original F matrix that we calculate. Note that the right bottom corner is 1, but when we normalize it, it has a relatively small number that is not so different from the other value from the matrix, so it's better. So here's the result for the normalized output, because like we normalize the output, it's like it shrink all the points into a small space and do the transformation, like calculate the fundamental transformation between the two small space, and then revert it, transform it back to the original image, and we can get a good result. The part 3 is the ransack F matrix. Basically, we need to find those filter points ourselves, and then discard the bad matches and only keep the good matches to calculate the F matrix, so we can have a good result of F matrix. So basically, the algorithm ransack is to randomly select some points and calculate the function, like estimate the fundamental matrix, and then we need to assess this, how good it is, by apply the F matrix to the points correspondence to get the good result. And I have multiple attempts to do this test, but one important thing is be aware of the typo, because if you do a typo, your TA will not tell you that, because TA is not responsible for your typo. And so that how I recognize I have a typo is when I test to pass the points to the function twice, and it gives the matrix that all the line is parallel and all the points are not the feature point on the second image, and I see, I choose a point from the first image and cast the coordinate to the second image, that causes that trouble. When I fix this, it have a relative, makes sense, good, not good, but relative good result for that. And also we compare the effect of the normalization and no normalization by the version 1 and the version 2, and we also have version 3 specifically for the last image, which has a lot of difficulty because there are so many similar features on different points, specifically on all the windows, because all the windows look exactly the same, and sometimes the algorithm will confuse which window corresponds to which window. So we adjust the threshold and the metric threshold and the example space, so we drew that. And here is the first try I do the ransack fundamental matrix. It has a lot of feature point. I have not select which point to use, which point I don't use, and it's centered in the scene, which is not right, because if the center is in the scene, it means the other camera is in the scene in the opposite direction to your own camera. That is not the case, because it's from the same side of the camera point, so they are from the same side, so there should not be a center point for all the epipole lines. Here's the version 1. I still got the epipole showed up in in the image, that is not correct, because that due to the noise. The noise will flick those lines up, and it will like generate a center point inside the image, which is not a good result that we want to see. And we need to find what caused that problem. Basically, there are one or two, because each time I calculate the fundamental matrix, I use all the inliers to calculate that. So if there is one inlier is actually not the inlier, it will mess up everything that I calculated. So here is a very obvious classic example for how it fuck you up. Basically, by single outlier messed up with your inliers. Here is the second version. You can see it has a very good line to the bottom left corner, and it's very good. I will be fast for all those. There is no outliers in my inlier set, so that's why it's provide a good result. Here is other image I test on, and they all have a good correspondence between the feature points. That's the effect of the RANSAC and the good fundamental matrix calculation algorithm, and it also have a good result. Despite there's only 30 points, I choose only the 30 best points to calculate this. Here is another one, but for the last image, it's don't have a good result because we cannot get rid of that inliers in the current setting, which has 1000 matrix threshold 0.001 for the epsilon, and for the iteration I use 5000 iteration. So I change the parameters. I change the matrix threshold to be 100. So there are some more feature points, and change the I don't change the epsilon, but I change the iteration to be 50,000. So it's 10 times the previous one. Although it took a long time, but it's get the expected result because our fundamental matrix algorithm is really good. It will do the work if you like to learn for reasonable step and learning rate and all the learning stuff, right? So here's a good result, and also I apply this to a previous custom picture set for the project 2, which is calculated anyway. It looks very good because I don't forgot what the project 2 is about, but this set of picture also have a lot of windows and the roof and the cars and a lot of different features, but it looks good in this project. Now is for the extra credit time. I'll show how I did for the extra credit. First, I do the checkerboard. I cap the checkerboard, and one thing I need to know is like checkerboard need to be asymmetric for the best result. That's why I cut my checkerboard. And the second is it works better if you have a large square size. In this picture, I only have a square printing on the A4 paper, and with a square size of 19 millimeter. That's very small size. It's like 2 centimeter, very small square. So it has a large mean error in each pixel. And here's a extrinsic parameter visualization. That's how I take this picture. Here is the result. And this is the second try. I reprinted the checkerboard and put it on my refrigerator and take 4 pictures, and here are the results. I see the first one has a large error because the square is small, second is print on the paper, third the bottom corners are not fixed, so it's like floating on the refrigerator. That makes the distortion, that makes the program thinking that this is not well calculated. It has a lot of error, but generally it's get the right position on the full image. So this is the result is good enough, but we need to prevent that problem when you want to calculate the serious camera calibration task. And here is the final result. And thank you for watching. Bye bye.